All right, so welcome to week 3 of data structures. Today we're going to be going back to the standard template library again, talking in particular about a class called the unordered map, which is basically C++'s implementation of a dictionary, which I believe you guys have covered in systems, or I'm sorry, in PG2, right? So, so basically, right, we've looked at a couple of different containers so far, right? We have covered the vector class, which is pretty much an array, right? A dynamic array. And then we've also looked at the list class, which is, of course, a linked list, right? Unlike the list class in C#, which is a vector, right? So it's kind of confusing there. So today we're going to look at a, like I said, a class that's going to basically be our dictionary, and we're going to talk about kind of how that works. And of course, we'll go into more detail on how it works on Wednesday when you guys will be writing your own dictionary, which I'm actually interested in any feedback you guys have about the order of things. So if like we did the vector lab and then we did the dyne array, right? So we used the vector and then you wrote like how an implementation of how it works. Do you feel that was the right order, or would it have made more sense if it was flipped around? So like you did the dyne array first, and then you kind of use the STL version after that. Okay, I mean, it's curious that everything is kind of very modular, so nothing really matters too much to me as far as the ordering. I was just curious there. So, all right. So today we're going to spend most of the time, or if not all of the time, just directly in Visual Studio writing some code. I have a general plan of what we want to do, but we're just going to kind of wing it, which is always the most fun for me, right? And so we can do some problem solving and things like that. So let's start out kind of talking about what the difference is, right, between some of the different data structures, right? So like I said, we have a vector, which is basically just a dynamic resizable array, right? And then we have a list. Let's make this like a tab, which is, of course, a doubly linked list. Right, so that's like a node-based type of data structure, right? And then we're gonna have this guy, which is called an unordered map, is the name of the class. It's kind of, I don't know why they named it that. They just did. There's some other data structures called map, which is basically a dictionary, right? So that uses pairs, right, where we have a key value type of system, right? So we're going to store things based on a key, and then it's going to have a value associated with it. So we look things up by a key, right? And so this is going to be very useful when we are dealing with very large sets of data. All right, because it's going to give us a faster lookup, and we'll talk more about that once we kind of get things started to set up here. Okay, so first things first, right, is we need a large set of data. So I have taken it upon myself to compile some data. It's not perfect. We're going to have to do some parsing through this file that I've created. But that's part of the fun, right? So I went through Wikipedia, and I made a list of every movie. So we have this text file that I wrote that's got, I didn't write, I copy and pasted it. If I wrote this, it would take me forever. But I got 34,000 movies here, right? Along with their date of release, right? Now, because I just copy and pasted it, it has some data in there that is not needed, so we're going to have to parse that out. For example, when I come down here, the way that they have their movies kind of broken up, if we go on Wikipedia, I don't have the page open anymore, right? They have little headers, right? So these are like, hey, all the movies that start with 2 and then 3, and then it has like A, B, C, etc., right? And even like broken down into like other, let's go down to like the A's here. So there's probably going to be somewhere around here. So like there's these little headers, right, for like, these are all the movies that begin with A, B through A, E, and then it goes through there, right? And then there's also some other kind of mini headers for like series of movies, right? So here we have like the Abbott Costello movies. They probably have like, you know, the X-Men movies and the Avengers movies and etc., right? So we're going to have to go through, because these aren't really movies, and we're going to have to take those out of whatever container we ultimately store things in. So let's go ahead first and try to see if we can isolate these movies out, right? So let's kind of write down a couple of things that we need to do, right? We'll make a to-do list here. So we're going to need to parse out non-movie data, right? So things like letter headers and collection headers, we'll say, right? And it also looks like, we go back over here, right? If there are multiple movies, like I guess this movie is named Abandoned, and there's there's 3 different movies with that name, right? There was one in 1949, one in 2001, and one in 2010. So we're going to want to see if we can parse out these 3 to make them 3 different entries, or we just use the first one and ignore the rest, right? So that will be something we need to at least consider, right? Is separate or remove movies with multiple years. Only use the first, right? So that would be something. I think those are the only 2 things that we really need to do, and then the rest of it is good, right? Maybe for these movies that have multiple versions, it looks like the syntax, right, is to have them have a colon at the end of the name. So we probably want to remove the colon there, because the name of the movie is not Abduction colon, right? It's just Abduction, right? This one, Abduction, the Megumi Yokota story, like that's part of the subtitle of the movie, right? So let's write that down, right? Remove semicolon if last character of movie title. All right, so let's go ahead and start to read this file, right, and store it somewhere. So we're going to need to include fstream right? Because that's how we open files. We're also going to include string, right? We could do everything with char pointers, but strings just make things easier, right? And that's not the focus here. So so it's okay to use the string class. It's not going to kill us, right? And then we're also going to need to store that in different places. I think I want to ultimately check like the timing on all three of these classes. So let's go ahead and include vector, list, and unordered map, right? Just so we can see which one is actually the fastest to look through a whole bunch of data, right? Okay, so so let's go ahead and first, what do we want to do? Let's make ourselves a pair, right? So we'll store everything in pairs, all right? So a pair is, again, something that has a key and a value. So what we're ultimately going to do here is we're going to store the movie title as the key, right? Because that's going to be mostly unique, right? With the exception of those movies that have multiple versions. And in fact, maybe just for simplicity, maybe we'll just take the first one, just so that we don't have any duplicate keys. Although it is allowed in the system, maybe we'll just do that. So maybe we'll just take the first one. So we have a key. The key is going to be the title of the movie, right? And then the value is going to be the year, right? So we'll be able to look up a movie based on its title, and then we'll be able to retrieve what movie that year, or what year that movie was released, right? So let's go ahead and create a pair, right? That'll have a string as its key, and then an int as its value, right? And what we're gonna do is we're going to make something called a type def. I don't know if we have gone over type def in other courses, I guess in just systems programming, right? But essentially a type def is kind of like an alias. So what I'm saying is that movie pair is actually one of these, right? Is a pair that has a string and an int. So if I make a movie pair called cur pair, right? We can see that it knows that it's a string and an int, right? There's two ways to do this, right? We can do it as the type def, which is going to allow us to get our IntelliSense and stuff, or we could do it as a pound define, right? Because a pound define is just a find and replace, right? So we could say movie pair is pair string int, right? And then that just has, it basically says anytime I see the word movie pair, right, I replace it with this. So it's just, do I want to do it at the preprocessor level, or do I want to do it at the compile stage, right? For data types, you probably want to do it at the compile stage, right? So type def is essentially just making an alias for a data type, right? This is going to just basically make it that I don't have to type this out in a bunch of different places, which I might not have to anyways, but just to kind of simplify things. All right. So let's go ahead and say that we're going to have a string for the current line, right? So we're going to read this file one line at a time, and then we're going to have to essentially parse that string to get all of the different pieces out of it, right? Or the two pieces, right? It would be the the name of the movie and then that first date, right? So, all right. So first things first, let's go ahead and open our file, right? So that's going to be an IF stream. And we don't need to do any of the binary stuff, right? So we're not doing binary because it is a text file, right? It's all in plain text. So that should be fine. Right. We'll close it up when we're done with it. We'll put all our code in between here. So read until the end of the file. So let's just make sure we can read to the end of the file. So while we're not at the end of the file, remember we have that EOF function, right? And so now I need to read a line of text. So, so there's a function called getLine, which will take in our stream, and then where we want to store it. This is a way that we can get info into a string, right? We can't really do that with cin, right? Like if I say like, hey, ifl.get, right? That's looking for, is that looking for a string? Or if I use ifl.getLine, right? It looks for a char pointer, right? Both of these versions, right, look for a char pointer as our first parameter, right? And a string is not a char pointer, but getLine is going to allow us to pass in a stream, right? So ifl and a string. So we'll say cur line, right? And then we'll go ahead and just print it out, right? So cur line, this is, we won't wait to see everything printed out. If it starts to print out, then it's probably okay, right? But this is going to print out like, 35,000 lines of text. So we don't want to do that. Okay, so it looks like we're printing things out, right? Oh, actually, it's moving pretty quick. We'll just make sure it goes to the end, right? And gets whatever that last name of that Zizix. This is not fairly new movie. I have not seen that one. Where are we at here? All right, there's Zizix. Okay, so we got that. Cool. So again, like typically, we want to write a little bit of code, check and see if it works, right? You don't want to start writing, dozens and dozens or hundreds of lines of code and then try it and see that like everything's, all foobarred, right? So, all right. So let's try and break this up now, right? So we're going to have our current title, and then we're going to have the current year, right? So, oops, we'll put some comments in here. Reading the line of text, and then this is where we'll splitting into different variables, right? Okay, so let's look at how this file is formatted, right? Well, actually, let's go ahead and see. Well, that's fine. So far, we haven't taken out these little headers yet, but we won't worry about that just yet, right? I want to see if we can split this up into, actually, I do want to do that now. So let's say, no, we won't worry about that. I lied. So how am I going to split this up? Okay, well, we know that we have some year at the end, right? So Are there any movies that have parentheses in the actual title of the movie that you can think of? Just scrolling through to see. Okay. Oh, here's one. So we have this movie, whatever this is, 500 Days of Summer. I haven't seen that one either. Right? Okay. So we probably want to look and separate out the last pair of parentheses, right? So let's go ahead and do that. So we're going to say, let me see how we do this. So, we'll say cur title. Let's see what kind of functionality we have in here, right? We can actually, where is string? Doing a little Google search here real quick. STL string. This is not what I want. This. All right. So I know that we have a function called a substring. All right. So let's look at this real quick. So substring, we'll pull this over here, right? It says copies a substring of some amount of characters. Okay. So let's see, how do we do this? Maybe this isn't what we want. So let's see here. So we've got some string, heterological paradoxes are persistent. So we print that out. And then we say we want another string that starts at 6 and goes to up to 7 characters. Okay, so that means that we can find out where, we'll minimize that, we can find out where that last parenthesis is. We know that every line has a parenthesis, right? Except for like these guys, right? These little headers that we're going to have to get rid of. So we're going to need to find this and then set our current title equal to sub 0 through the end, that the index of this minus 2, right? Because we want to go up to this. Right? Let's see how that works. Experimentation. So we'll store that in an integer, right? So we'll say location index of last open parens. We'll make it very very explicit there, right? So we'll say index of last open parens equals cur line dot find last of that. And then we'll say cur title equals cur line dot substring starting at 0 up to index of last parens, I think -2. Because we want to get rid of the last parens and we want to get rid of the space as well. So let's see how that works. So instead of printing out cur line, let's print out cur title. Again, we don't have to print out the whole thing, right? So maybe we'll just set a breakpoint here so we can run through this line by line, see what happens, right? So what did I print out? Okay, I'm not printing out what I want to print out, right? Let's come back over here. Run it a couple times. All right, so yep, I should have maybe just done -1. I don't know what this extra garbage is at the front. We'll have to figure out what that is. So let's do a -1 here. Just run through this a couple times. Okay, what's this? What's this garbo at the front? So let's go up to the top of our file. We have, what is that? It's just like some extra junk. The rest of them look fine, but this one has some junk at the front. I don't see any junk at the front of my file unless it's like invisible text enchantments. I don't know. Is my code magical? Is this file magical? I don't know. Let's see what happens if I open. This is open. This is basically Notepad. Okay. Well, what does this say? Arithmetic overflow using casting the result. Cast it back to an int. Go back to that. I don't know what that first one is. I mean, I don't think we're going to be looking for this movie, and I don't want to spend a whole lot of time like working on this. Wow, we have a bunch of. Oh wait. There's this stuff, which is. So it looks like these are French movies. Okay, so we can't display this, right? We're not in, console is not Unicode. So that's going to be a problem, right? For characters that we can't display, right? Unless we can maybe change our properties here and change it to something that I don't think we can change it to a let's try this one more time. Did not like that. Let's go back up here. Yeah, so it looks like there's just some extra garbage in some titles because of foreign characters and whatnot. And then that first one, I don't know exactly what the problem is with the, right? So let's go ahead and go back to whatever the standard thing is, consolus, so it doesn't look weird, right? So, all right. So let's go ahead and also parse out, what is this warning here? Overflow in a 4-byte variable. because substring takes in a size underscore t, so let's change that to a size underscore t. All right, so we've got that, right? And now we will also, we need to move the date over into this integer, right? So that we can ultimately make a pair, okay? So let's see how we would do that. Okay, so we know that, let's see, what kind of functions do we have for our string again? Let's go look here. We can get, okay, let's try. See if this function will work. Let's see what copy does. Well, that's going to copy into a chart. What's a value type point? The target. No, I don't want to copy into a character array. That seems like a lot of work. I want to take. Guess I can copy. I know where the first parenthesis is, or the last parenthesis rather. I know that each date is going to be only 4 characters, right? Because we don't have any movies from like the year 15,000, and we don't have any movies like prior to whenever they started making movies, like in the late 1800s. So we know it's going to be 4 4 characters, right? So we can go ahead and kind of move that into a per year string, right? So that would be current line substring, right? Which would be our offset, which is going to be index of last parens plus 1, right? And then we've got 4 characters there, right? So let's see if that worked. So we'll say per year string, put a new line in there, run this and see what happens, right? All right, so we're looking pretty good, right? With the exception of like some symbols in movies, right? Like I assume this is 9.5 weeks, right? This is 8.5, which is a movie by Fellini, I think. Federico Fellini, Italian film. So, but we won't worry about those, right? We could fix that if this was a larger project. So, cool. We've got our 2 things set up, right? So now we need to add them into, let's say, a vector, right? So we'll say setting up a couple of containers. So let's make a vector that stores movie pairs, right? And we'll call it movie vec. Right, and then let's say only parse actual movies. So we'll say if the per line dot find last of that. Nope, that's not the right function, is it? Find last of is not equal to this character called the end pause, which is basically kind of like the end, right? So if we go through a whole line, right, and we don't find a character or a parenthesis rather, then that means that it probably was not a movie, right? Because it doesn't have a date. So let's print those out. So cur line, and let's not print out here, right? So we should just print out the stuff we're trying to strip out now. So let's see how that works. Right? So it looks like, right, we're getting like just like the series and then just like the kind of like these headers, right? Like MA through MAB, MAC through MC, etc. Right? The Kung Fu Panda series, right? Looks like maybe there might be a couple of movies in here that aren't formatted right on Wikipedia. Like I said, I didn't clean this up or anything. I just like literally like copy and pasted things out, right? So so there might be a couple of movies that we strip out, but I think, you know, we'll still get the gist of things, right? Get rid of this warning here. Should get rid of that warning. Maybe not. Okay. So cool. So now if we didn't have it in there, then we can add to the container. So we'll say movie vec dot pushback, right? And we want to pass in a movie pair, right? So we'll give it the current title, and then we need to give it the integer, right? Which we only have as the current year string. So we're gonna kind of convert that into a an int, right? So we're gonna use this function here. Let's make sure that this works. So we'll just say, actually, we'll do this as a separate loop here after we close our file. What do we have? Vector of movie pair, colon, iterator, iter equals movie vec dot begin, iter not equal to movie vec dot end, plus iter, cout, iter, we can use iter arrow first, iter arrow second. So within the pair class or struct, or however it's set up in C++, instead of actually using the terms key and value, they just use first and second. So this is the key and this is the value, right? So this should be the name of my movie. This should be the year. All right, let's see if this works, and then I'll explain this little block of code here. So, all right, so looks like it's working. We're not removing that colon there, so we'll want to go in and remove that as well. We can do that up here. So, as I said, right, the year is actually stored as a string, but I want to store it as an int. I guess I could store it as a string as well, because like it really doesn't matter if we're just printing it out, right? But what I'm going to do here is I'm going to take this function from the string class called C_str. Basically what that does is it returns the char pointer that's stored inside of my string, right? So it actually like returns my string as a char pointer rather than a string, right? A class. And then I'm going to use this function here, which is a C function called A2I, which stands for alpha to int. So basically it takes a char pointer that consists of digits and it can convert that into like its actual numeric content, right? So like the string, you know, like 2003 actually becomes the integer 2003, all right? So, so I create a movie pair, right? And this is my key, and this is my value, right? And we'll go in and say, remove the colon if it is the last character, right? So we can say, hey, if cur title sub cur title dot length -1 is equal to colon, then we can erase the offset, so cur title dot length -1 and 1 character. That should work. Let's see. Let's see if that works. So how are we going to test that? I'm going to comment this out up here, and I'm just going to put in a couple of couts here, right? So we'll say, hey, cout cur title, tab, cout cur title, new line. Just erase returns a string, so let me reassign it there. Okay, so it should. All right, so that looks good, right? So we have like the Italian job colon, and then the new one is just the Italian job, right? Okay, so looks like we're in a good place so far. I'm going to go ahead and copy over the timer that we used the other day just because I know we're going to need it. I believe that was in lecture 4. There we go. So we'll bring this over into this so that we can do some comparisons between the different things a little bit later on. Right? So now we can also do this with our list class, right? Movie pair, movie list. I guess I can go ahead and do this, right? I can say something like this. So we'll make a movie pair called cur pair. And then we can push back cur pair. Right. That, why does this not work? Because I don't have a semicolon there. And then we can also do movie list dot push back current pair, right? Because that is also our same method, right, to add into a list, right? So now I'm storing all of my movies inside of a vector. I'm storing all of my movies inside of a list, right? So then we can do some kind of A/B comparison here at this point. Might as well get some input here. So we'll say, let's make a, can you get information directly into a string? I don't know. It's been a while. So enter a movie title. cn.get. Is it taken? Let's try it. We can use get line, right? cn and user input. Okay, and then we will say timer dot. We need to make a timer, right? So let's make a timer. So we'll say doesn't know what timer is because did not include the header file. All right, so timer dot start, right? And now I need to find the movie in my vector, right? So finding the movie in the vector, right? So movie vec dot, let's see, there's no find or anything like that in here, right? So we're gonna have to look through the vector, right? We're gonna have to do an order in search. So vector movie pair colon iterator iter equals movie vec dot begin, iter not equal to movie vec dot end. Right, seen this before many times. And we'll say, hey, if iter first is equal to user input, right, meaning it's the same string that they typed in, right, then we will say iter first was released in iter second. And then we can break, right, because there's no need to look through the rest of the list, right? And then we can do timer dot stop, and then timer dot elapsed, right, to get how long did it take to go through that. Okay, so let's see if this works. All right. Let's clean up some of these warnings we have. All right. What is this? Check pass out to an int. Will that clear up that warning? Sure did. All right. So here we go. Took a couple seconds to read in that file. Enter a movie. So what movie should I look for? Let's try something that doesn't have a lot of like maybe a different way to spell it or space it out or anything. So let's just try, I don't know. What do we got here? Let's try Men in Black. All right. All right. So it found Men in Black in 7 milliseconds. Right. So not bad. Right. Let's test this out also in our list. Right. We should basically be able to do the same thing in the list. I don't think the list has a find or anything either, right? So it doesn't have a find method, right? So we're basically going to have to do the same thing, right? Finding the movie in the list. So copy and paste that down, right? We'll say list, and this will be movie list. Movie list, right? And let's throw a couple of new lines in between these. we'll say something like finding in list, and we'll put finding in vector up here. Right, so remember, right, with a vector, it's just an array, right? So we've got all of these like tens of thousands of movies in our array, right? And we are going one index at a time until we find our movie, right? With a linked list, it's a node-based data structure, right? So we have a whole bunch of movies, right? Tens of thousands of movies, but they're located at all different places in memory. And so every time the iterator moves, right, it moves to a different node to look at, right? So functionality-wise, it looks very similar, right? But that's because the standard template library tries to make things easy, right? So we'll use Men in Black again. All right, so it's about the same, right? It's not going to be the exact every time, right? So we got like 9.5 milliseconds versus about 9.5 microseconds, right? Or 9,431 microseconds, 8,147 microseconds, right? If we run it again, right, it might. So we saw it swapped there, right? So they're about even as far as time is concerned there. All right. So any questions about what we've done so far about like parsing this file? I know you guys have done text file parsing before, correct? Okay. So now let's look at this new thing called the unordered map. All right. So the unordered map, right, wants our I think we have to actually pass in the two different things, right? So we're storing pairs, but the unordered map requires us to pass in, right, a couple of different things, right? We have to pass in our key type and then our value type. And then we also have some other things that we can pass in. But if we don't, they're kind of filled in for us, which is what we're going to do today. And so one of those is the hash. And so let's talk about, well, actually, you know what, we're just going to do it first, and then we'll talk about how the hash is able to do what it's able to do, right? So so we will just go ahead and say that our key is a string and our value is an integer, right? And I'm just going to call it a dictionary because that's pretty much what it is. All right. And so we are going to now add it in movie dict dot. Okay. So we don't have push back here. All right. If we go through the list of all of the functions that we have here, right, it's all alphabetical, right? There's no push back, right? Because this is not like a linear type of container, right? Where we have, right, when I add something into my vector, right, they're in that vector in the order that they're added in, right? When I add things into the list, they're entered into the list in the order that I add them in, right? So the head pointer is that whatever that first movie is, like the $5 million problem or whatever that one was called, right? And then the last, like the tail of my list is that Zizix or whatever, right? This one uses an insert function, all right? And we're just going to insert in, we can just pass it a pair, right? So again, we can just pass it the current pair, right? And now, now we've got we've got everything in these three containers now. Okay, so now we'll go ahead and kind of copy and paste this little section here, and we'll say finding in unordered map, which is a dictionary, right? And this is not going to need a loop. All right, so this is going to, I'm going to take an unordered map, string int, colon, iterator. Actually, it's a, I think we can just use a regular iterator. Call iter, and we're going to use, what do I call it? Movie dict find, and we're going to pass it in our string. So that is, what do we call it? User input. All right. So if our iterator is not equal to movie_dict.end, right? So this is, it basically returns what, it returns our object, right? Or an iterator to our object. And so if it goes through our whole dictionary and doesn't find our object, then it will return basically an iterator that points to the end of a dictionary, right? It means that it's not there, right? So it's kind of like the same thing that I'm doing up here, right? I'm going through, I'm comparing, is it the list, right? And then if I get to the end of the list, I move my iterator all the way through my list and I don't find my object or what I'm looking for, right? Then it's not there, right? So that's what this find function kind of does, but it's not a loop-based approach, all right? And we'll talk about the details of that here in just a minute. So again, we can go iter arrow first was released in iter arrow second. Whoops, how did I do that? All right. So we'll try it and true. Men in Black. I don't know. It was on the shelf here. So, all right. So I've got 8.5 milliseconds to find it in my vector. 9.5 milliseconds to find it in my list. 0.3 milliseconds to find it in my unordered map. All right, so that's a massive difference in timing, right? So that's, you know, let's try another movie, make sure this isn't a fluke, right? So what do I want to look up? I want to look up, I'm looking at my movies back here. We'll look up something that's close to the end of the list, maybe. So we'll look up like Teen Wolf. All right. So that had to go through the vector and through the list a little bit more, right? Because that's further into those data structures, right? And that's why it takes a longer amount of time, right? But we can see here, like, that took a little bit longer, right? But not substantially, right? This is a substantial difference between whatever it was, 8 or 9 milliseconds to 12 milliseconds. You know, this was like, you know, about 8 or 9 milliseconds to 17, right? That's almost twice, that's like twice as long. And this like increased a little bit, right? Like if we try something that's like even further in the list, right? look, I barely took any time at all, right? Extremely, extremely fast to look up our data, okay? Excuse me. So how does it do that? All right. So it let's actually write some more code down here to kind of take a look at things, right? So let's say size of, or let's say capacity of MovieVec. All right. So we know how a vector works, right? That every time I add something to the vector, right? If I've reached my capacity, then we are going to reallocate a larger array and then copy things over, right? So we're gonna increase our capacity each time. With a vector, it's gonna increase that capacity by a rate of 1.5. All right. So we'll say size of MovieVec, right? So we'll say this is like the number of elements that we have in there, right? So and then we can do size of movie list, movie list dot size, right? And remember, lists don't have that extra overhead, right? We don't create additional nodes that are empty, right? Like we do with the vector. So the size of the movie list should be just the number of movies that we have allocated, right? It should be the same as the size of MovieVec, right? So if we run this, we'll get to the unordered map here in a second, right? We'll look up Zombieland again, right? So in our MovieVec, right, we're storing 33,500 movies, right? But we've allocated almost 41,000 elements of space, right? So I have this a giant array that's got 41,000 elements in it, right? And we could trim that down, right? We have that function called shrink to fit. If we wanted to remove that extra memory, we could do that, right? And our movie list, of course, is the same. These are all nodes, right? So I've got 33,500 nodes, and we only have that many nodes, right? We don't have any extra nodes just like hanging out waiting to be filled in like we do with the vector. All right. Now with the, let's put a new line in between these like this. Dictionary. All right. So the size and there this I think I want to use this. All right. So we have, well, we should probably put another line here. So we can see that that was a very large number, right? Zombieland, right? So, how come we don't have 30 there? Am I not using the right function here? This is should be this should be size. What is this function? Not giving me back what I want it to get back. Where is size? Size. Turns the length of the controlled sequence. Okay. So let me. Okay, I think I know why it's giving me that number. Will cause you need to explain some things here. Check one thing real quick. See if we can get gets the size of a bucket. So it's the bucket for a key value. Can I get my bucket count? Per bucket. Okay, let me check this function here, and that will hone me in. I'll just put it at the end. RubyDix.max bucket count. Let's see if this gives me a number greater than 1. That will. That is definitely a number bigger than 1. That is not. No, that's not the function I want. That's the maximum. Oh, that's the maximum number. No, I wanted max load factor. That's what I wanted. Max load factor. I know you guys don't know what any of this is yet. That's okay. Huh. All right. So how are we not getting all of this content in here? It should. Okay, well, not sure why it's not giving me the same number. It's not exactly what I thought it would be, but that's okay. So how is it able to go and find data so quickly? All right. It uses what's called a hashing function. Have any of you guys heard of hashing before? Besides like besides hash browns? Right. So
at a table. Oh,
okay. So a hash function, right, is basically where you take your data, right, and you run it through some algorithm that spits out a different set of data, right? So this would be when you have a password on a website, right, or on the Xbox or PlayStation, right? When you type in your password, they run that through a function, right? And so that turns your password into some other set of characters, or maybe even a numeric value. And then that's what's actually stored on the server, right? So like if we said, hey, my password is password, right? Because I'm not very secure, right? Then it runs it through some function and it turns it into that, right? And that's what's stored on the server, right? Or it might turn it into, something like that, right? And, so that's what's stored on the server. So they run your string, right, through some algorithm, right? Usually they're fairly nonsensical, right? Like they're fairly complex, but they're fast, right? Because they need to be able to do this all the time, right? So you don't want your hashing function to be slow, right? And it returns ideally some new unique set of data, right? And so that's what's stored on the server, right? So I type in password, they run that through a function, and they get this, and then they compare it against that on the server, and if those two strings are the same, then they let you into your account, right? Typically, hash functions on for passwords and things like that are what they call a one-way hash, meaning that there's no possible way to go backwards, right? So even if someone hacked in and got all of the encrypted user data, right, they would just get this. They would say like, hey, Justin's password is this, right? But they would have no way of reversing that back into my dumb password, which is password, right? So that's a one-way hash. And so what the dictionary does is, if we remember, right, we'll go ahead and type it in again. When I make an unordered map, right, then it can take in a function, right, that will be a hasher, right? And if I don't pass anything in, then it just uses a built-in one for whatever my type is. So it somehow is taking my string, right, and it's converting it into, in this case, a number, right? So if we say like, hey, Zombieland, right, turns into that. All right, so it does something with my string, and it converts it into a number. That number corresponds to an index in my dictionary. And so now it's just more than likely an order one lookup, right? It doesn't have to iterate through the whole vector to find where I need to be, right? Just to, go through every single movie until it hits Zombieland, right? It doesn't have to iterate through the list, or through the list rather here, and go through every single node until it finds Zombieland. It just looks at my string, says, oh, Zombieland. If that is in the dictionary, this is the index that it's found at. And so it goes to that index, and then it just does a comparison there, right? And it says, yes, it's in there, right? So we can see that when we come in here, there's some other functions, right? We have movie dict dot, what was it? Was a load factor. So this load factor function basically tells me, when we come over here, right, we can look this up, right? Counts the number of average elements per bucket. All right, so we'll get more into buckets on Wednesday, right? But essentially, this is a gigantic array, right? It's like, what is it? It's like 65,000 elements. So it's 65,000 elements in my array, and each index of that array is a linked list. All right. So if I have multiple keys that equate to the same hashed value, right, and it takes me to that same index, then I have a linked list that I can run through to compare against, right? Now that linked list ideally is going to not be storing much data, right? It's going to store ideally one thing, and that's what this max load factor is it's saying like, hey, you know, this is the maximum number of elements per bucket was 1 for us. But we can see here when we run this with our load factor, right? We can see, let's try a different movie. We'll try like Jurassic Park. Right. So, right, we have 33,000 movies in our dictionary. Like, I don't know where like these 500 movies disappeared to. So, and we've got 65,000 elements in that in that dictionary, right? So that means that only 50% of the elements in that have anything in them, right? So dictionaries are not good if we're worried about memory usage, right? Because we're using a ton of memory here, right? They don't have a way to really see what the actual memory usage is, right? I guess maybe yeah, I'm not sure. I don't want to open up a task manager and do all of that nonsense. But we're using a lot of memory, but we're getting this huge benefit of I could find whatever I need to find in basically an order one search, right? Out of 33,000 something items, all I have to do is I immediately, after I call my hashing function, go directly to the index where my data is located, right? I don't have to iterate through anything. I don't have to, do a binary search, right? Which is a log in algorithm that would be, fairly efficient, but order one is the most efficient, right? Constant. So in a worst case scenario, right, if we had our hashing function be not as good, then we would be looking at maybe having a handful of items in that bucket, right? So we would go to the bucket, whatever, bucket 14,000 or whatever, and there would be a linked list there, and it would have like 5 things in it, right? So we have to look through those 5 things to figure out which item is actually the correct one, right? But that's a worlds apart from iterating through an entire vector or iterating through an entire list, right? Like, you know, what index is Zombieland located at? I don't even know. Let's find out, right? So we'll say index equals 0. Index plus plus. All right, let's say cout index. All right, so if we look up Zombieland, right? There we go. So that was an index almost at the end, right? 33,450 out of 33,555, right? So that's like the last movie in my collection. I don't even know if I have that movie anymore. As you can see, I've got like a bajillion movies behind me that I'm just pulling data from. So, so that's like way far in the list, right? So it takes a long time to iterate through there, but long, like as far as the computer's concerned, right? Like 18 milliseconds. That's like nothing for us, right? Like we can't even like really like even time that. But this, right? That's like a quarter of a millisecond to find it in the unordered map, because it doesn't have to iterate at all, right? It just says, hey, you know, it's at this particular bucket and we're done, right? So we can probably figure out what bucket it's at, right? Let's take this part out because it's kind of not correct. So I believe, let me see how we can find it with our bucket. Bucket equals, let me see if I remember how to do this. Movie dict dot bucket wants a key val. Okay, so I can just give it the bucket, which would be user input. Right. I think we've already done this, or we found this number before, right? So it was found in this bucket 44,498. So that's essentially like the 44,000th index, right? So there are a bunch of buckets that don't have any data in them, right? Let's see if we can figure out how to iterate through all of our buckets. I think there's a way to do that. Movie dict dot bucket size. What does it want? It wants a size underscore t, which is the bucket. So let's look up this function real quick. Bucket gets, that gets the bucket number. Let's see, bucket size. Let's do a bucket size. So it wants just a bucket number. Okay, so we know that there are 65,535 buckets because that's what it told me there were. So we'll just loop that many times. That might be the max number of buckets. No, I don't think it is. I think because your lab tonight uses more buckets than that, I believe. And we'll print out movie dict dot bucket size I. Let's see what this prints out. Should get like a bunch of zeros and then like some ones. We'll take this out. So, okay. So there are some buckets that have two pieces of data in them, right? So if whatever bucket this was, right? I don't know what bucket that is. Let's actually print that out. So let's go cout. Let's see if we can print out the data that's at that one of these buckets that has two in it. If we can. Okay, so 986 up here, right, has 2 pieces of data in it. So let's remember 986. And let's see if we can figure out how to access the data at that bucket. All right, so I believe we have a function called, that just gets us the number of buckets. It gets me the bucket number. Okay, that's not what I want. Can I get... There might not be a way to do it. Let's see. Gets the bucket number, gets the number of buckets, gets the size of a bucket. See begin. For iterator range. No, I don't think that's going to do it. Finds number of elements with the matching key. Might not be a way to get our data from a particular bucket. Counts the average elements per bucket, gets the maximum number of buckets. Yeah, it does not look like we can actually get that data out from what I'm seeing in these functions. So, but there are some buckets, right? A bucket is an element of our giant array, right? That is storing 2 pieces of data, right? So that means that 2 movies got run through some hash function and resulted in the same number, right? And so when I go, if we figure out, if we knew what that movie was, right, and we did a search for it, then what would happen is it would go to that index of the array, right? And then it would say, it would look inside of that index, there is a linked list. Okay, so it's going to look at the first node in that linked list and say, is this the movie, right? And it says no, and so it goes to the second item, right? So the second node, right? So it moves over one node, and it says, is this the movie I'm looking for? You say yes. Okay, cool. Then it returns, the iterator returns that movie, right? So therefore, right, the I only had to look at two pieces of data, right? So I hashed, I got what index my movie was at. I looked at the first movie, it wasn't that. I looked at the second movie, I found it, right? So out of 33,000 movies, right, of 33,000 pieces of data, I only had to look at 2 of them, right? If the movie wasn't there, right, like if I hashed to some other movie that's not in the list, right, then that's what this check does, right? I went through my whole list and it didn't find it, right? So, I wonder if, no, we don't know how to do that. Okay. So, all right. So that's what makes this so fast, right? And so when we're dealing with large sets of data, right, this is going to really be very efficient, right? And we don't necessarily, right, in our case, right, if we scroll back up to the top here, right, we're looking at, right, a string, right, the movie title, and then we're getting the year, right? But it could be obviously something more than that, right? Like if we were to think about this in a databasing terms, right, then if I go on IMDb or whatever, right, and I type in Zombieland or Avengers Endgame or you know, Lord of the Rings or whatever, then it's going to basically we can think of it as equating to the same thing, right? It's going to look up our string, and here it probably gives us like a URL, right? So that we can go to, that's going to have all of the data, right? With like the year of release, the cast, the director, you know, the trivia, the reviews, and all of that stuff, right? So this could be, you know, as much data as we want it to be, right? It could be a class, right? So, you know, if we wanted to have this, and it doesn't always have to be a string, right? The key could be anything. So it could be like an int, right? So it could be like, hey, it's your student number, right? And then it pops over into a student object, right? And it has access to, you know, your name, your contact info, your grades, any other info that gets stored internally here at Full Sail, right? You know, or it could be, you know, your social security number, and then it pulls up, you know, your records for your taxes at the IRS, right? So your key values can really be anything, right? Okay. Any questions on this? I think we've kind of covered it, right? There's not a whole lot of functionality in this, right? It does a lot, but you don't have to use like a ton of different functions in order to do it, right? Basically, right, it's just like insert and find, more or less, right? We called insert, we passed it in a pair, right? And then we called find, right, to find our movie. And that's those are like the two key functions, right? You know, we use some of these other ones like size and bucket count just to kind of show you how much memory we were using there. All right. So any other questions before we go over and start looking at the lab? I know, like, we only spent about an hour and a half here, but I don't know what other functionality we have to go over. Unless there's just something else you want to see me try to do, or something else just in general code-wise that you need a better explanation on, we can go over that as well. All right, then I guess we'll bounce over to the lab for tonight, and then if there's any questions about that, then we'll jump back over here. All right. Okay, so for tonight, we're going to be messing with Scrabble, right? The board game Scrabble. And I'll actually pull this up just so that we can see it in here, right? Hopefully you guys know what Scrabble is, right? Like, so it's a board game, right, where you're creating words, and every letter in that word has a value, right? And so and then you score based on, you know, how many points your word was, and like more uncommon letters have a higher value. Like a Z is 10 points, right? So if you can create any word that has a Z in it, then that letter will score you 10 points. And then there's There's other things. There's like double and triple letter and word scores, and we're not going to worry about that. Okay. So what we're going to have in all of this, in all of these unit tests, right? Set up exactly the same as we've done before, right? With our DSA defines, right? So we've got, right, a series of pound defines, right? And it'll run a test. So you'll see that. You should be used to that by now, right? So we're going to have 2 data members in this class, right? We're going to have an array of letter values, right? So that's going to be, right, the scores for the individual letters. Like I said, like Z is 10, etc., right? So we're going to use this function to populate that array. All right. So over in the unit tests, I'll be passing in those an array with those values, right? And so that's going to come into this array, and you're basically going to assign each index of this array into the corresponding index of that array, right? So we have 26 letters, right? So index 0 would be whatever the score for A is. Index 1 would be whatever the score for B is, etc., right? Index 25 would be Z, right? So that's that function. This function here, right, will retrieve the value of a particular letter, right? So, so this function, we're going to pass in an uppercase letter, all right? And you are going to return the value from that index, right? So like if I pass in A, you're going to return whatever is at index 0, right? If I pass in B, you're going to return whatever's at index 1, etc. All right. So, so that will require some math within this function. It should be a fairly short function, like 1 line, but it will require some math to do that. But it's not too complicated. You may have actually encountered this in one of your earlier classes. I'm not 100% sure. All right. Next up, right, we're going to continue along this path, and we're going to get the value for a word, right? So, so basically we have our string, right? Remember, a string can be accessed just like a char pointer, right? So you can use the brackets to go through each individual letter in that string, right? If you're using some type of loop, they have a dot length function that will let you know how long your string is, right? So we don't have to pass that into the function, the length, because we can go ahead and get that through one of the methods in the string class, right? So we'll return the value of the word, right? So like if the word was like at, right? Everything's going to be coming in uppercase as well, right? Then like at would return 2, I think, because A's are 1 point and T's are 1 point, right? If it was like bat, then that would return, I don't know, like 4 or something. I don't know how much. I don't know. Remember off the top of my head what the point values are. I guess we can look them up real quick in the test suite here. Moving down to okay, so B's are 3 points, right? So that would be like 5, right? Because B is 3 points, A is 1 point, and like T is 1 point, right? Because it's a very common letter. All right. So that's that function. Right? Next up, right? Just kind of a helper function to create a pair that you'll be able to use once we get to actually like getting into the unordered map portion of things, which will be down in these last two functions. All right. So basically we'll create a pair, right? So a pair that's going to have a string for the key, right? So the key is going to be the word, right? And then the value is going to be the score for that word, right? So like bat would be 5, right? So we're going to go ahead and create a pair with this word as its key, and then you'll figure out what the word value is, right? Well, you have a function that can do that. If you want to call that function again, then that'll work, right? Then now we're gonna, these last two functions will be used to we'll use the unordered map, which we have called Scrabble map. All right. So for this here, this function here, right, we're going to load a file containing all of the Scrabble words along with their values. All right. So you're going to need to, this is the file that's passed in, right? So do not, in this function, hard code in the name of the file, right? Open this file with your file stream. So you're going to open this file. And this has all 178,691 legal Scrabble words. All right. So if you're ever playing Scrabble, you could use this to determine any particular word that is legal in Scrabble, right? So, so you're going to open that file, right? You're going to create a pair, right? That's going to contain the word, right? The word that you just read, and the value for that word, right? Which you'll have to figure out what the value is. You have a function that does that. And then you'll insert that into your Scrabble map. All right. And then the last function kind of wraps everything up, right? So, so if this function is going to find a value in the map, right? This is going to make use of some of your previous methods. So you will have to load the file again inside of this function. Remember, because all of the unit tests are modular, they don't assume that you've written anything else yet. The only way I could figure out how to do that right now is to just have you hard code in words.txt, because I didn't want to pass in the name of the file again. I guess I could have done that, but I didn't. So we're gonna, maybe I'll do that next month. So we'll pass in the, so you'll open this file. You can just hard code that in this particular function, not in this function. And you'll populate your letter values using this array, right? So again, you've got the functions that do these things, right? Then you will look in your map, right, to find the score for that word or -1, and then you'll return it, right? So you'll look in your map, right, using find to find that word, and you'll return the score for that word, right, which would be the second part of your pair, right? If the word is not found, then we'll return -1, right? So if I try to pass in a non-legal word, something that's not in your map, then you'll return -1. All right. Any questions on any of this stuff? Or again, anything else that you guys want to cover for the next, however long you guys want to hang out? All right. And as you guys know, hopefully you guys have seen that announcement, right? That I updated the DSA Labs project with this lab, right? And the dictionary lab that you guys are going to do on Wednesday, and the BST lab, which is Friday's lab. So you'll want to make sure that you grab that either from the lab project activity, which I updated, or that announcement that I sent out last night. So, all right. And I'll put up this this code that we just wrote. I'll put that up on Discord here in a minute while I start uploading this this video. So, all right, Deshaun says he's ready to go. Hopefully, I tried to make this lab kind of interesting. I had this idea kind of rolling around in my head for a while, so hopefully you guys enjoy it as much as I did writing it. Yeah, it shouldn't be too bad, I don't think. But of course, that we're here to answer any questions you have, right? Phil will be available for lab at 5, which is in about 2 hours. So, all right. Well, if there aren't any other questions about anything programming related or data structures related, then we'll go ahead and call it. But I'd be more than happy to keep going if you guys have some ideas about what we can do.
I got in at the tail end of this lecture, but I think I'm stuck on the usage of hash functions.
Okay. So, so as I had mentioned, right, like there's kind of 2 uses for a hash function. One is for like encryption, right? For like passwords, right? When you type in a password on like a website or on Xbox or PSN or Steam or whatever, that text that you type in, right, is going to get put through a hash function like a meat grinder, and it's going to mangle your password into something else. Some other string or unique value, and that's what's actually stored on the server. So they'll compare that mangled password to the mangled password that they store on the server. So that way, if someone hacks into Steam or whatever, they're not going to be able to get everyone's passwords, right? Or they're not going to be able to get everyone's credit card information, because all of that stuff is hashed through what they call a one-way hashing, which means that there's no possible algorithm that could unhash it back to the original value, right? So they do something with that text which makes it where it cannot be reverted to its original form. We'll take a look at some hashing functions on Wednesday when we actually are writing our own hash table.
Yes.
Um,
Mhm.
so
Well, can I just step in right here and just be like, because at first it was sounding like the hash tables would function something like how we use hex numbers and like, red, green, and whatever the other color is to distinct uh, for colors or whatever, right?
right,
And this is seeming like it's one way, like you put in what it originally was, and then the function is like a machine, and it spits out something like you would change a hex code, right?
right.
And then, but how does it get reversed? But or how does the next step understand what it was from the beginning? Like, how do the hash function do that?
Okay, so with a hash table, right? So what it's doing with our if we go back to our movies example here, right? When I type in um, Zombieland or Men in Black or whatever, right? It's going to hash that string into an integer. All right, so it's going to take that string and perform some calculations on it, and it's going to give me an int value. Okay, that int value represents what index that movie would be found at in my table. We call it a bucket. So what bucket that movie's at, right? So I type in Zombieland, it runs it through some hashing function, and we get 44,612. Okay, so then I get an iterator right here. I get an iterator to that um, that bucket. All right, so this is now an iterator that's going through a linked list. Okay, so then it's going to look through that linked list and compare each node in that linked list against the original string Zombieland, against my key value. Okay, so and then when it finds it, it'll print it out, right? So this is basically saying like, hey, you know, find my data, right? So this function lets me know what bucket to go to, and then um, it's also going to go through that list until it gets to the actual data. Does that make sense, Glenn?
Yes.
Okay. So again, we'll diagram some of this stuff out on Wednesday, and maybe it'll make more sense. That's kind of why I was thinking about possibly switching the order of these lectures to where you do write the class first and then use the STL version. So like write DynaArray, then do the vector, because then maybe the STL version will make more sense. That's something I might toy with testing out next month. I have not decided yet. So everyone said like there haven't been any problems going this route. So it seems to be working out okay, but I'm wondering if maybe the other ordering might be better. Right. So something to toy with on my end. Um, so um, so there, yeah, we'll definitely go deeper into the actual nitty gritty of how hash tables work next lecture, right? So now we're just kind of using it, seeing how fast they can be, and then we'll get into the details of how we can actually make that a reality on our end. Our version probably won't be nearly as efficient as this unordered map, right? Just because we're going to try to keep things relatively simple at this point, you know, if we were to go and look at the unordered map code, it would probably like look fairly hellish to most of you guys, maybe even me, right? In fact, we could go open that code up and look at it, because template classes can't have CPPs, right? So we can see the whole file, right? So if we go and look at find, maybe it might actually be, so let's see, find hint. I don't know what find hint is. Can I go to that definition? Go to, that's not the definition. Yeah, we can't actually look at the actual code, right? We can only look at like this code, which is not that helpful. I don't know if maybe what's this function, x hash. Okay, so here, right, we can see like kind of some hashing functions, right? So they are going to, if it's using this, right, so it's like, hey, the hash value, right, it's gonna like test to see whatever this does. It says something about is pointer, right? And then I'm gonna take my key value, right, and I'm going to use exclusive OR, and I'm going to exclusive OR it with this hexadecimal value dead beef, right? And the U is for unsigned, right? So the unsigned hexadecimal value dead beef, right? And that is what that's going to do. You can see like some of these other hashing functions, right? Like that's the only hashing function I really saw there, right? But they do like just like really like strange things. You can look up some hashing functions, and we'll look some up on Wednesday as well, right? But yeah, so you want to take whatever your data is and generate a unique hashed value. That way each element, right, only has one piece of data in it, so that you can find anything in an order one search, at the expense of taking up a lot more memory, right? So, but usually, like if you have a large database, then memory is not really your concern, right? Like, you know, if you want all of the movies or all of the words in Scrabble, right, then you know that you're dealing with, you know, tens of thousands of things. So you want to make those lookups as fast as possible. Then a dictionary unordered map is definitely the way to do that. All right. Any other questions? All right. Well, then I guess we'll see you guys on Wednesday. Again, lab starts at 5. So Phil will be available. This will be the first time he's dealing with this lab. So if you have any problems, just hammer him with questions. And we'll see you guys on Wednesday. Take care.